So let me start by saying that, yes, I do work at Mila, but I have a big love for physics. Actually, my studies were in pure maths. So you don't be, if you see that I say strange things from time to time, or I say things that are unusual for physicists, please forgive me. And just bear with me till the end. Hopefully you would like what you see. At Mila today, well, it's an institute for machine learning. I am trying to use machine learning to simulate quantum systems in faster ways, and at the same time I'm trying to see if we can use quantum mechanics to actually improve neural networks and all that kind of stuff. So the topics here. So I will just introduce in 2 slides standard quantum mechanics. I don't have to teach you this. You guys know this better than me, I'm sure. Then we will go through what we call nowadays the Wigner Monte Carlo method. This is actually a Monte Carlo method to solve the Wigner equation, which is an equation which is equivalent to the time-dependent Schrödinger equation. And why we did that was that at the beginning we were very interested in this Wigner equation, and we implemented this Monte Carlo method, but only a few years later we realized that all of these could be, let's say, expressed in terms of a formulation, in terms of postulates, which you could use to define a quantum system. And right after that, we will see this signed particle formulation. And eventually, at the end, I would like to show you a few benchmarks and applications. The reason for that is that the first time I presented this stuff at the Bulgarian Academy of Science, where I implemented this approach, there was one academician that stood up and say, "Hey, this is impossible, you cannot do this." So I started to play with the formulation and applied it to a plethora of different situations just to show that the formulation would give the right answer. So eventually, out of this, I got in 3 years more than 30 papers, which never happened in my life before. I was very surprised, but it's a very interesting, I mean, it's a very productive formulation, I would say. I mean, in just 3 years, all these papers, I am not even counting proceedings and things like this. And it would be, for those of you who are interested in seeing the implementation details, just to see how this thing works, there is a source code on this website here. The interesting part of this source code is that actually the code is very, very short, which means that this theory has something to say. When I was a PhD student in Italy, my teacher was always telling me that nature must be very, very simple. And the simpler the theory is, the closer you are getting to nature. And I don't know if that is true, but I believe so. I think there must be some value in this sentence. So the fact that this source code is very, very short must mean something to me. So how did I end up with quantum mechanics? I will just give you a short background just to let you understand. So essentially, I started with pure maths, but when I had to start my PhD, my tutor told me, okay, you can't do pure maths if you want to have food on your table every day. So you must do something different. And he proposed me to deal with semiconductor devices simulation. So for a while, this is what I have done. And the interesting part is that what people have done, what engineers have done in this field is that they have come up with some, let's say, I mean, to make a very, very long story very, very short, they come up with some design of a transistor, and what they were doing was to shrink the dimensions of those transistors to have more and more transistors on a silicon chip, so you could get more computational power. But at the very end, you cannot shrink your transistor in that particular design forever. It doesn't work. At some point, you start to see quantum effects appearing, all kind of stuff, and the transistor do not work anymore, so you have to come up with a different design, and for that, you need a theory. So there are many, many challenges, actually. in this kind of devices when you are, let's say, when you are playing with length channels which are of the order of a few tenths of nanometers. So one of the challenges is that now the wave particle duality start to appear. So you cannot treat particles just as classical objects as they would do before. So you have to treat them fully quantum in a full quantum approach. But at the same time, you don't want to play with you don't want to simulate things in a ballistic situation because this is not realistic. Electrons in semiconductor devices feel a lot of external events, and especially one of these is what we call the phonon scattering events. And this is something that would be very, very complicated to embed let's say, in standard quantum mechanics. If you take, say, the Schrödinger equation and you want to include those effects, you can do this on a piece of paper, but if you implement this in a computer, you'll see it doesn't work. I mean, it's very, very slow. And if you exploit other formulations like it has been done in the past, like, for example, what they call NEGF, non-equilibrium green functions, it's same story. You have the scattering terms. They are all very well known. You can write them on a piece of paper, but again, if you put them in a computer, it's extremely slow. And actually, when you play with green functions, you cannot even access the transient regime. You can just do things in a stationary regime. But in those devices, we are not sure anymore if we reach a stationary regime or not. So we have to have a time-dependent approach. So there are many, many different challenges that appear in that context. So this got me interested in quantum mechanics. I started to see if there was some approach that could embed all these phenomena at once. So if I could have some model that would include all these things, and playing with a lot of different formulations, eventually I got this formulation that I am discussing with you today. So standard quantum mechanics, this is, I don't want to teach you anything here. This is just to make sure we are on the same page. And this is the way I personally understand it. I don't know, theoretical physicists might see this as an oversimplification, I don't know. But more or less the way we see it in the field of semiconductor is that you need a wave function to describe your quantum system, and this is a complete description of your system. And then if you want to do you want to make a prediction, you use this wave function and you apply a heuristic rule which is known as the Born rule. And observables are represented by operators, which is something that works, but it's not very intuitive, I would say. Sometimes it can create troubles. And you have two equations to study a quantum system. You have the time-dependent Schrödinger equation, and you have the time-independent one. Okay? Of course, this is not the only formalism available. There are many others. For example, before Schrödinger, Heisenberg created his own formulation, which is based on density matrices. Well, the Schrödinger is based on wave functions. Wigner is based, for example, on quasi-distributions. You have the Feynman formulation, which is based on path integrals, the Keldysh, which is based on green functions, and so on. And then eventually we have today this one. I mean, it took me some years to be able to publish this thing, which instead of using, let's say, these mathematical objects here, is using Newtonian particles which carry a sign, which can be a plus or a minus. But I will go through the details. So we will start from the Wigner formalism. I don't know if you guys are familiar with this. Usually when I present this stuff, if I present this to applied mathematicians or engineers, they are not even aware that there are other formulations. So sometimes I just show what this thing is, and I will do exactly the same way we did for the Schrödinger formulation, just 2 slides. So in the Wigner formulation, you don't use wave functions anymore. What you use now is a quasi-distribution function. And we say quasi because it's not really a distribution function. It can have negative values, as you can see in this nice picture, for example. And, but the very interesting thing about this formulation is that every observable are represented exactly in the same way as in classical statistical physics. So you take the quasi-distribution, but even though you know it's a quasi-distribution, you use it as a distribution. So it's interesting because if you are familiar with classical statistical physics, then you can get familiar to Wigner in just a few minutes. It comes for free. You don't have to make any effort. And of course, in the Wigner formulation, you have the same story. You have a time-dependent Wigner equation, and you have a time-independent Wigner equation. This is not exactly an eigenvalue problem. This is what they call a star eigenvalue problem or something like this. I can't remember. But more or less, this is what you have in the theory. Sometimes people tells me that this must be some approximation of the Schrödinger equation. This is not the case. The time-dependent Schrödinger equation and the time-dependent Wigner equation are mathematically the same. I mean, you have a transform that brings you from one formalism to the other, and this transform is invertible. So whatever prediction you can do with Schrödinger, you can do also with Wigner. And yeah, and that's the transform, the Wigner-Weil transform. So, well, maybe I didn't choose exactly a nice formula here, but essentially the message to take here is that if you have a wave function, you have this Wigner-Weil transform, and you can transform your wave function in a corresponding quasi-distribution function. And if you have a quasi-distribution function, you can transform it back to a wave function. And this has been shown, this has been proved mathematically in this paper here in 2004. So the two formulations are completely equivalent. What are the advantages of this theory? Well, the first advantage that we saw was that it's an intuitive language. I mean, even if it's in terms of quasi-distribution functions, it's not that bad, especially if you want to simulate semiconductor devices, for example. Usually you are coming from a semi-classical background, so you are familiar with things like Vlasov equation or the Boltzmann equation. So if you know these things, then the Wigner equation is very, very intuitive, and it's very, very close to classical statistical physics. At the same time, those effects that I was talking about a few minutes ago, these inelastic effects coming from phonon scatterings and things like this, can be included in the time-dependent Wigner equation very easily. So you can write it on a piece of paper. At that time, we didn't know if we could implement this in a computer. Eventually, we found out that yes, we can do this, and actually with very, very small computational resources. So this is another thing that I would like to underline. And another very important point is that you can include general boundary conditions in this formulation. When you play with the wave functions, usually you know that you set your wave function to be 0 at the boundaries of your system. So essentially you are describing a closed box. But semiconductor devices are not closed box. They are open boxes. You apply leads, and you have a transport of electrons through these systems. So you cannot really use Schrödinger formalism unless you know how to include open boundary conditions. There are papers which have tried to do this, and they are very compelling, actually. The problem, again, is that computationally speaking, if you try to implement those approaches in a computer, again, you need an immense amount of computational resources. While here it's not the case, you can apply pretty much any boundary conditions. I will actually show you, and this thing always works. So the Wigner-Monte Carlo method. So since at that time, several years ago, we saw that the Wigner equation could bring some advantages, we decided to focus on this equation. But the problem with this equation is that, as you can see, it doesn't look very nice. Mathematically speaking, this is integral partial differential equations. This is horrible to treat analytically, but even numerically, it's no piece of cake. And here I'm reporting, okay, the terms Q here, which is the right-hand side of this equation. You see again, you have an integral here, and inside you have what we call the Wigner kernel or the Wigner potential. And again, here, this is another integral. So no wonder that even if this formulation appeared just a few years after the formulation of Schrödinger, nobody used that. I mean, it's an intuitive language, but what can you do with such equation? So for quite a while, nobody has been playing with it until in the 90s, some engineer started to play with this equation. And what they did at the very beginning was to apply the finite difference method to this equation. So they would take it, it's this very long equation, they would discretize it, and they would get a way to solve it, okay? The problem with finite differences, and actually you have the same problem with finite, with any finite framework, is that, let's say for example, finite element framework, is that this term here that you have in this equation, as you can see here, this term here, that we call the diffusion term, cannot be calculated correctly by discretizing it in a finite framework. And why it's like this? Because this term here oscillates very, very rapidly. So whatever mesh you come up with, eventually this thing will oscillate so fast that whatever mesh you started from won't be enough. It won't give you the right resolution you need. And so in the 90s, they tried to do things like this. They obtained promising results, but eventually you had 3 or 4 papers with different methods based on finite differences, and they would give different results. So of course they abandoned this thing and they tried something different, but it didn't work, and eventually we come up with this idea. So at the Bulgarian Academy of Science, the funny thing was, well, the interesting thing is that there you still have people that used to study in the old Russian school, and it's a very interesting environment because you get exposed to ideas that probably you've never seen before. It was my case at least. So they introduced me to a method which was heavily used under Soviet Union and which was completely forgotten after that. And this method was a Monte Carlo method which would solve whatever equation, but by sampling, having samples which would carry a sign. This method cannot be applied to any equation, of course, but it can be applied to any equation which can be written in the form of what we call a Fredholm equation of second kind, which is this thing here. Okay, so I won't go through all the details, but essentially whatever equation you can write in this shape, then there is a theorem that tells you that the solution of this equation can be written at least formally in terms of what we call a Liouville von Neumann series. Okay, and if you can write the solution in this way, then you can apply this Monte Carlo method based on sign sampling. So since my ex-boss there was actually a student of Kolmogorov, and he was an expert in Monte Carlo methods, we decided to apply this to this equation and see if it would work. So how did we end up in writing the Wigner equation in this shape? I will skip a lot of details. I mean, I can share the papers with you if you are interested in the mathematical details, but it's I mean, it's a lot of details. It took us months just to find out how to apply this Monte Carlo method in this context. But the story goes like this. The first thing that we found out was that if you take the Wigner equation, I mean, we were thinking in terms of semiconductor devices all the time. So we were thinking, okay, we don't need to deal with an infinite spatial domain, because those devices are finite, and actually we don't even need to treat every momentum in the phase space, because many of the particles you would have there, or let's say many of the electrons you would have there, they would stay more or less in a range of momenta. So we thought that it could be interesting to discretize the space of momentum in the phase space, or the space of pseudo-wave vector, which is practically the same thing, okay? And if you do this, you come up with this equation which looks a little bit nicer. So this is still the time-dependent Wigner equation, but this time you are introducing the fact that you have a spatial domain that goes from 0 to this L here, and we discretize the momentum space. So no big deal so far, but this simplifies the mathematics greatly. And at the beginning, we just wanted to see if this Monte Carlo method would work on this equation. So we took, let's say, we took the simplest way to check that. So what happens is that if you do a little bit of algebraic manipulation on this equation here, now that it is on a semi-discrete phase space and a finite semi-discrete phase space, you can rewrite this equation in this way, which now starts to look like the Fredholm equation of second kind. Now, if you see here, there are still a lot of details here, like for example, now we have this gamma function that appears here, and this gamma function is defined this way, but we have also a capital gamma function that you see here, which is defined this way, and so on. So there are still a lot of details that I am skipping, but the idea is to retain is just that you can write the equation now in this way. And if you do this, and you take what we call the adjoint equation of this equation here, you end up with an equation which is exactly the Fredholm integral equation of second kind. So you can write the solution of this equation now in terms of this Liouville von Neumann series. So now that we know this, formally we can write, let's say, the mean value of any macroscopic variable which we are interested in terms of a series again. And what you see here, okay, maybe this doesn't look familiar, but if we go through the mathematics, you will realize what I mean. I mean, this A of xm, m here would be momentum, x would be position. This is your microscopic definition of the macroscopic, let's say, it's the function that defines your macroscopic variable which you want to find the mean value of, okay? And what we report here now is this sum here, which is the sum over this FW that you see here. So essentially your Liouville von Neumann series is here. And what we do here is that we are simply integrating over this function times the quasi-distribution function to find the average of this microscopic variable here. And here I am skipping a lot of things, but I hope you bear with me and you trust me. If you now start to write the first few terms of this series, you start to realize that there is a pattern that repeats itself all the time. And the pattern is like this. Well, here I'm reporting just the term 0 and the term 1. The second term is actually very, very big. But if you write the first three terms, and you put them all together, you start to realize that there is a way to interpret physically what's happening here. And if you take the other three terms, then you realize that it's the same story again. And if you take the other three, it's again the same story, and the same story. So there is a structure here that is branching all the time. And again, I apologize for skipping all these details, but it would take literally hours to go through them. Once they invited me in Belgium to discuss about this, and they wanted to know all the details, it took 2 weeks every day, 2 hours of seminars. Okay, so that's why I'm skipping the details. I mean, I'm not hiding anything. So the story that we find here, that, I mean, it's not very, very clear from that, but what we get at the very end is that this gamma function that we just saw before, this gamma function here can be considered as a particle generation rate. And exactly what we create here is that, I mean, if you take the first three terms, what you see is that if you take, let's say, one of these particles which have a sign now, these particles from time to time, according to the gamma function here, they will create a new couple of particles, one with a positive sign and one with a negative sign. Okay? And these particles now will carry a sign which essentially encode the quantum of information that is encoded in the system. Particles in this context here are Newtonian, so they have a position and a momentum simultaneously, but they are fieldless. So if you assign a momentum to those particles, they will keep this momentum forever. But from time to time, they will create these couples of sign particles, and this is the way you evolve your system. So all of this, it's a lot of mathematics, so I have been thinking for quite a while, and at the end I came up with 3 postulates which explain all this, and in my opinion it's way simpler. So I will show you now these 3 postulates. This is in the single body context. So the 3 postulates are the following. So I'm doing here the Star Wars order. I first say number 1, number 3, then you'll see number 2. Okay. But I'm doing this because these 2 are much simpler than this postulate here. Okay. So how does it work? Now physical system, I mean postulate 1. Physical systems are not described by wave functions anymore, but they are described by an ensemble of particles which have a plus or a minus sign. Okay, and there is a way through the Wigner-Weyl transform to go from a wave function, for example, to a corresponding ensemble of signed particles. So this is another detail that I am skipping, but if you are interested, I can share the papers. So yeah.
You're creating these particles with plus and minus. Are they correlated in terms of momentum and position, or are they just totally?
They are, well. If you take let's say if you take let's say you describe your quantum system initially, you describe the initial conditions of your time-dependent quantum system, and say you start with a wave function. Okay, so what you can do is that you take the wave function, you apply the Wigner-Weyl transform, and this gives you the quasi-distribution Wigner, the Wigner quasi-distribution. And this quasi-distribution is not going to be positive everywhere or negative everywhere. So what we do is that according to this distribution, we create an ensemble which would reconstruct this quasi-distribution. And you are going to add a negative sign to those particles in the negative areas of your quasi-distribution. So more or less, this is the story. And again, I'm skipping details, but if that makes sense, I'm very happy with that. So now you have any physical, let's say any physical system can be described by means of these virtual Newtonian particles. I'm saying virtual because they don't really represent anything, or, well, it's a tricky, yeah, it's a bit tricky. And these particles now, they are always provided with a position and a momentum simultaneously. The only difference with, let's say, Newtonian mechanics would be that these particles have a sign. They carry a sign that they carry forever. It never changes. And postulate 3 is telling you that if you have 2 of these particles with opposite sign, but in the same phase space position, they annihilate. So their contribution is 0. So postulate 2, this is a very nice thing here. Postulate 2 tells you how to evolve those signed particles now. So we now know how to start from, let's say, initial conditions, whatever they are. we know that if we have two particles in the same position of the phase space with opposite sign, they don't contribute, but how do we evolve them? So imagine, for now we are just putting ourselves in a situation where we have a single body. Okay, so just to avoid any confusion, when I will say particle, I mean sign particles, and when I say bodies, it means, say, electrons in a device. Okay, so there is no confusion. So in the single body context, you suppose that you have a potential which is defined over your device or your domain, and this is a function that is depending on the position, right? This is the way we do in physics, and and I am keeping it simple. I mean, we could also treat, for example, time-dependent potentials, but to simplify the whole thing, I'm just presenting this condition here. So in this context, if you have this function here, which represent the potential applied to your body. What you do is that, first of all, you are going to compute what we call the Wigner kernel, which is this thing here. As you can see, this is not a nice integral here. As soon as you increase the dimensions, it becomes difficult to compute this integral. But actually, we found different ways of doing it. So, for example, if you are in a relatively small, space, you can use finite differences, and it works. But if you increase the space, then you can use, for example, we've been using important sampling Monte Carlo methods there, and it works. But since I arrived in Montreal a little bit more than a year ago, we started to play with neural networks, and we also found ways of exploiting neural networks to compute this integral, and actually it works very well. The thing is that you obtain more or less the same accuracy with neural networks, but it runs 18 times faster. So it's an interesting point to underline. So once we have the Wigner kernel, say we have a way to compute it. It could be even an analytical way if we have a nice potential. Then you can compute this function here, which is going to be let's say the generation rate that we saw before. And the way we compute it is by this integral, which I had to define. I mean, it's not exactly a Riemann integral. Actually, it's not any kind of integral that I have seen in mathematics. So I had to come up with my own definition. And I call this thing nowadays a momentum integral because it looks very, very similar to path integrals. And actually from there, I think there must be some connection with the Feynman formulation, but I had no time to investigate. But so the main message to retain here is the following. So you have the potential here, you compute this kernel here, and then you compute this gamma function. This gamma function is going to tell you now when your particle and where it's going to create those couples of sign particles. And once you create those particles will have exactly the same position as the parent particle, but the momentum will be determined stochastically. And the way you do is by exploiting this probability here, which is the positive part of this function here, over gamma, which now becomes a normalization factor. Okay? Well, hopefully everything is clear, so I will go ahead. And the same story goes with many body. I mean, once you figure out the details in the single body context, it's trivial. I mean, it's really trivial to generalize this thing to the many body context. And the way eventually we published this thing was that you still have postulate 1, 2, 3. It's just that now they are generalized on let's say a bigger phase space. Now your phase space is 2 times n times d dimensional, where d is the dimension of your spatial domain, so it could be 1, 2, 3. Then 2 is because you now have your particles which have a position and a momentum, and n is the number of bodies. Okay, so you are just doing exactly the same rules, just that now you apply them to points with a sign which are defined on a, let's say, n-dimensional phase space. Okay, but it's exactly the same story, and we were very, very impressed by that at the time, because this was another thing that famous academician told us would never work. When I said, okay, I want to generalize this to the many body systems, he said, okay, you're never going to do anything like this. And eventually what happened was that it was trivial, and we found that the postulates are exactly the same. I mean, you see now the gamma function is not defined over the one position, is defined over n positions. And your momentum integral here, it's a multidimensional integral, of course, which is defined by this very, very nice formula here. But again, it's the same story. This is a generation rate. I mean, you can interpret this as a generation rate, and you can interpret this thing as the probability of assigning a momentum to your just created particles. Okay, but it's exactly the same story. And this was a very, very, very nice result to find, because it simplified our life once we wanted to start to play with many body systems. The classical limit, this is something I have to apologize. I mean, it's very interesting, but I can only show a summary, because again, it requires a lot of mathematics, but I can share the papers with you guys, no problem. So if we now take these postulates and we say, okay, what happens when h bar tends to 0? You know, the classical way of going to classical physics. So the first thing that you can show, and that's pretty easy, is that the creation of sign particles is now prohibited. You will always end up with a gamma which is identically 0, which makes sense, because let's say in classical mechanics, you don't have sign particles, nothing like this. And certainly you don't have creation of sign particles. Then the particles, you can show that they are not fieldless anymore. They feel now the potential that is applied on the domain. And negative particles are not allowed any longer. They are completely prohibited if you try to do the math. And the very interesting result is that you can show that those sign particles, which now have just a plus sign, so no big deal, their equation of motion coincides exactly with Newton's law. So it's a pretty nice result, actually. But I couldn't go through all the details, so forgive me. And again, if you are interested, I will share the papers with you. So some applications now. So, of course, the first thing that we wanted to do was to compare with Schrödinger equation and see if we would get the same results or if we would get different things. Actually, there was a group in the US and there was another group in France which have been playing with Monte Carlo methods applied to the time-dependent Schrödinger equation for a while. And although they would get very promising, very interesting results, once you would apply their method, let's say, to a situation like that, and you would compare with the Schrödinger equation, you could see there were some relevant differences. But this is not the case with this formulation. I have papers where I show this, and the agreement is very, very good. So, for example, in this case here, we start from a wave packet that is localized here, and we push it towards this barrier here, which represents a potential barrier. So what you expect is easy here. You expect that part of the wave packet will scatter back, and part of the wave will tunnel through the potential. So at 20 femtoseconds, this is more or less what you see here. You start to see that now there is a structure that is shaping up here, but here you see that there is some tunneling happening. And if you go ahead now, the tunneling is even bigger, but now you have those structures that are being created, and eventually this thing scatters back to the position, to its initial position. But all of this is very nice in the real space, but it's even more interesting in the phase space. Because now you can do quantum mechanics in phase space with signed particles, and it comes for free. I mean, every particle have a position, have a momentum, and has a sign. So you can reconstruct them as ensembles, you plot them in the phase space, and you see what happens. And for example, here, it's exactly this experiment here, but in the phase space. And what you see, I mean, imagine now that we have a wave packet that is initially localized here, and has a momentum that is pushed towards this red line, which represent the position of the potential barrier. So what you see is that after some time, this wave packet now is very, very close to the potential barrier, and you have some oscillations happening here. But after some times, you start to see that now part of this wave packet is going through the potential barrier. I mean, now here it's very, very clear, but part of this wave packet, if you take into account that this is a momentum space and this is a position space, part of this wave packet now is going, it's trying to acquire a different momentum. And as you can see here, it's almost symmetric in the sense that the initial momentum that you had here is more or less the momentum that is trying to acquire to scatter back, okay, which is something that you would expect. And after some time again, what you see now is that there is a very, let's say, very clear wave packet here, and you have some wave packet here, and at the very end, this is what you get. So you have part of the wave packet that went through the barrier and part of the wave packet that went back. And these oscillations that you see here, these oscillations are very well understood in the phase space in the Wigner formulation. They means essentially that there is some entanglement between these two wave packets, which makes sense because they started as a one wave packet. And if you do the very same experiment, but this time you put a very, very high potential barrier, what you expect, of course, is that you won't have any tunneling through the barrier, or you will have just a little bit of tunneling. And what you see here is that the wave packet had an initial momentum, then it starts to find its way towards a negative momentum. Here it's becoming even more clear, and here it's very, very clear that the wave packet is just getting back with this new momentum which has an opposite sign. Eventually you come up with something, you end up with something like this. So let's say the use of these signed particles is very interesting because you can also do quantum mechanics in the phase space, and it gives you a wealth of information that you wouldn't have in the configuration space. So it's a quite interesting situation. And then, okay, we wanted to apply this thing to a many-body situation, so we started with the hydrogen atom, which is kind of understood, so we know how things should behave there. But we wanted to do something a little bit more interesting than the usual. We wanted to consider the whole hydrogen atom as a two-body system. So your proton is a quantum object, and your electron is a quantum object. Okay, and of course, what you expect is that the wave packet of the proton is not going to do a lot because it's a very massive object compared to an electron, but still it's interesting to see what happens. So say we don't know anything about the initial conditions, so we just put two Gaussian wave packets at the beginning, and these two Gaussian wave packets, of course, they are centered in the same position. Okay, and we let this thing. So and of course, what we do is that these two objects interact through their potential. So if you simulate this thing as a two-body system, this is in the space, and this is what we call a reduced phase space. You can see the dynamics. So this is at 0 attoseconds. So this is initial conditions. Then at 3 attoseconds, you start to see that the proton packet here is slightly getting bigger, it's spreading, but nothing more than that. But the wave packet of the electron here is a completely different story. It's starting to split in two parts. And if you let this system go ahead, at 6 attoseconds, you have something very interesting. Now you start to see that there are two peaks here and here. And if you simulate this system for quite some time and you do an average of the wave packet and you do the distance between the center and one of these peaks, what you get is the Bohr radius. So, which means that this many-body formulation must work. I mean, it provides the right answer at least. And of course, we wanted to do more, so we decided to apply this to an H2 molecule. And same story here. What we did was, okay, we take now, okay, we say these two, let's say these two protons are very far away, and then we get them closer and closer and closer, and we see what happens. And if the formulation is correct, it should show you that there is the formation of a bond. Otherwise, again, there is something not working. And of course, what you see here, so this is a cut of this two-dimensional image. If you do a cut here, and if these two protons are far apart, then the wave packet corresponding to the electrons, they are very localized. They stay far apart, and nothing happens in the middle. I mean, there is noise here, but this is due to the stochastic nature of the approach. But if you get them very, very close, then it's a completely different story here. Now you start to see that there is the creation of a bond between the two. And just to make sure that this method was providing the good results, we also compared to a DFT simulation. And if you do this, I mean, it's pretty difficult to find any difference. Yes?
So how does this deal with the identical particles?
You mean indistinguishable particles? I have a slide about this. I will go.
I have a question. In quantum field theory, you need equation annihilation operators.
Yes.
And you need a vacuum. So you have to have a Fock space, and you annihilate the vacuum or create particles. And that leads to quantum electrodynamics, which gives you the Lamb shift, which is known to be very accurate experimentally. So how can you, maybe you're just restricted to quantum mechanics. Yeah. You're not doing quantum field theory.
No. But
still, you have created annihilation of particles.
So actually,
that's still, strictly speaking, quantum field theory. These are things. Because you have a photon decaying into two positron electron.
Okay.
And you need quantum field theory to do that. You can't do it with quantum mechanics. No.
Well, to be honest, I am not familiar with the quantum field theory. So.
But you talk about.
Yes, I know. But let's say if you are talking about second quantization, those operators there, these are very different objects. So I can see there is some similarity, that's for sure, but I never investigated how far we can push the similarity.
So this is really just mechanics. Yeah.
It would be interesting to do this.
The way quantum field theory is constructed is very specific rules, especially with the vacuum. And I don't see how you
probably can't.
I have no idea, to be honest. But we can discuss about this later if you like. I mean.
Go on,
Okay. But I mean, thank you for the idea. I mean, it would be interesting, that's for sure. So to go ahead, after doing, so of course I'm showing you just a few validation tests that we have done. I mean, we have validation tests in 30 papers, so you can imagine it's plenty of validation. But then we wanted to push this thing towards systems that could not be simulated by the Schrödinger approach or any other approach, and see what this formulation would tell us. And one of the interesting things that we wanted to do especially was to study, for example, the resilience of entanglement between particles, resilience against, let's say, environmental noise. So if you're in the ballistic case and you start from initial conditions like this, so this is again the phase space, and those are two wave packets, and what you see here, these are oscillations which represent the entanglement between these two wave packets. The first thing to do is to simulate this system in a ballistic case, because in the ballistic case we have exact solution, and we know that in this case the only thing that you should see in the phase space is a rotation of your system. So this was the first test that we did, just to make sure that the method was able to deal with this kind of situation, and as you can see, it provides the right answer. But then the interesting part is the following one. There are experimentalists around the world who want to play with entanglement in semiconductor devices, and they want to exploit this entanglement. The problem is that when they play with those things, they have to play, you know, in vacuum rooms, well, let's say in huge machines where they essentially lower the temperature to 20, even less millikelvin. So it would have been interesting to see if there is some form of entanglement which would be resilient to the vibration of the crystal lattice. So we simulated exactly the same thing, but this time we decided to add some noise to the system. And external perturbations here, it's very, very simple to do, because you have particles with a position and a momentum, so more or less you know what to do there. So we decided to apply this, and we applied this to different situations with different kind of entanglements. Like, for example, in this one, you see that you have very narrow oscillations and they go very rapidly. But here you have oscillations which are not very varying very rapidly, and they are kind of spread. And another situation which is in the middle between the two, you have an entanglement which is characterized by rapid oscillations, but these oscillations are wider in space. And if you simulate these three different systems with the same scattering effects, you can see which one is going to have entanglement. I mean, which one will keep these oscillations after some time. And this is something that you cannot do with any other formulation, to the best of my knowledge. I mean, I never seen anything like this around, to be honest. And if you do this, for example, so of course you see that there is some rotation again, which is what you would expect anyway in the phase space. But this time you see that these oscillations are somehow disappearing. Like, for example, here it's very clear that the situation is very different now. And the winner in this test is this one here, where you have still positive and negative oscillations, and they are still very clear. So there are ways to play with this theory and actually make predictions like this that would be very difficult to do with any other formulation. So this was something that was published in, I think, 2 weeks when we sent that. It was accepted right away. And to conclude, we have also been playing with the systems of fermions and bosons, because the three postulates that I've shown you in the many-body case, we can prove mathematically that they are valid. These three postulates are valid for both fermions and bosons. And actually, even when you consider your fermions as indistinguishable objects, the three postulates are still the same. I mean, this is something that can be shown mathematically. And so in this case, we are now in the normal space. And we have, let's say, these two wave packets here, which, well, they overlap a little bit. And the experiment here is the following. You have two wave packets which represent, say, two electrons, and you push them one against the other. and you want to see what happens. And of course, we know that there is a principle called the Pauli exclusion principle. You shouldn't be able to push them in the same position. If that happens, your theory is predicting things which are not correct. Okay? So in the real space, what we see is that so after some time, we let this system evolve and we see, okay, something is happening in the middle here, but these two peaks are not going in the same position. After some time here, the peaks now are starting to be very, very clear, very localized, but still they are separated. And after some very, very long time, you still see that these two peaks are separated. So this means that the theory is providing the right answer, but it's way more interesting in the phase space, because now here you are going to see that the Pauli exclusion principle is really embedded in the theory, and it comes for free. So now you imagine that you have your very localized wave packets in the phase space. So this is position and this is momentum, and you push them one against the other again. And what you get here is at some point, okay, there is something happening here, but the two wave packets, I mean, at least the red parts here, which is the most interesting part, they are far apart. And after some time, you start to see this ring here. And you have a very high probability of finding particles on this ring, but nothing in the middle. Actually, I should have put a color bar here. You would see that this thing corresponds to almost zero. So this ring here is what we call a Fermi hole, and this is a signature of the appearance of the Pauli exclusion principle. So
each of these two particles, if these are two electrons,
these are two electrons.
So they have electrical charge, and they're each.
Yes, you consider the system as a two-body system. So they are not separated. You have a quasi-distribution function which is defined over the position and momentum of the two particles. And what you do is that you use those signed particles to evolve this quasi-distribution function.
Yeah. But how would I distinguish? Suppose I start off with two particles, like say two electrons, but now I'm going to swap them out and I'm going to put two ions.
Okay.
All right. So now we have bosons,
yes,
which are both charged. So
yes.
Like the electron, except now they're bosons.
Yes.
And they, because they're bosons, they want to be in the same quantum mechanical
yes.
state, but electrically they're repelling each other.
Well,
so how do I distinguish between the electrical repulsion, because I've got the charge, and the exchange symmetry that probably.
This is a very good question. I never been thinking about this. The only thing that I can say here, I mean, as far as I understood, during the development of this theory, is that bosons and fermions will follow exactly the same rules. But what will define a system of fermions or a system of bosons is going to be the initial conditions. So.
I don't think that's.
We can discuss later about this. I mean, it's a very interesting question. I don't have all the details and all the answers, but we can discuss later for sure. And to conclude, since at that time everybody was interested in semiconductor devices. I don't know if you are aware of this, but around the world there are physicists who are playing with single atoms of impurities. So they are able to put, for example, say phosphorus atoms at a certain position at a very, very high accuracy. And what they do is that by playing with such systems, they are able to do some quantum computing, at very low temperature, of course. So the interesting question here was what this theory can tell us about systems like this. And so imagine now that you have a three-dimensional box, and here I'm doing a cut just to show the potential that is created by the phosphorus atom. And here again you have this wave packet which represents an electron that is going through this lead and is going in this direction. Okay? And we start from temperature 20 millikelvin. So we see what happens. And you see that after 10 femtosecond, this electron now is very, very close to the phosphorus atom. But if you go at 20 femtoseconds, it's practically sitting on the atom. And eventually here, this is a top view, you see that the electron is leaving the device. But now let's do exactly the same experiment, but at 300 Kelvin. And what do we observe? So now, at 10 femtoseconds, the electron is still here. Nothing much is happening because you have scattering effects now, so it's losing energy. And if you go ahead, at 20 femtoseconds, this thing now is very, very wide in the device, but still, let's say, the center of this packet is not even close to the phosphorus atom, which is something you would expect. And at 30 femtoseconds is a completely different story than what we saw before. It's just spreading. So yeah, so this was just to show that we can tackle problems which are interesting from an experimental point of view, and which would be extremely complicated to simulate with other formulations. Actually, this is another paper which was accepted right away. I mean, this never happened to me. Usually I would wait 1 or 2 years for a review. And after that, I even had a reviewers complimenting, congratulating for the approach. So there must be something in this theory, and that's why I wanted to share it with you guys. So conclusions. Personally, I would like to see more applications, especially in quantum computing and quantum chemistry. This is exactly what I'm doing at Mila in Montreal. But it would be extremely interesting to do some theoretical investigation here. And this is something that I cannot do on my own because I don't even have the skills to do this. And that's why I wanted to present that to you. So, of course, I'm open to collaborations. And even if you don't want to collaborate, if you like this approach, please spread the word. And thank you very much for your attention.
So I guess to summarize what you're saying is that you want to propose an alternative interpretation of QM. So if that...
An alternative formulation.
Formulation?
Yeah.
Yeah, okay. So in that case, what you want to do is that maybe you want to check the spectrum of applicability of your formulation and compare that to what we already have.
Yeah.
Right? So when your entire formulation is based on the Wigner Wild.
It is based just as the Wigner is based on Schrödinger.
Well, okay, yeah. So, well, I mean, mathematically speaking, they are two different, I guess, slightly different paths of quantization schemes: deformation quantization and geometric quantization, and they have sort of like a slightly different range of applicability. So, what I'm thinking is that there are some like subtleties, mathematical subtleties, in the way that you're constructing your those gamma functions and your those v's that you're defining at v plus, especially when you're just taking the positive part of your v, that can change the regularity of your v.
Yeah.
Yeah, which means that when you take the Fourier transform, you might get something weird, you know. And when you want to integrate that, in addition, on top of that, you might get something undefined, right? But on the other side, when you take the same potential and do things with a Feynman approach or something,
yeah,
you get something right. You get something that
it
makes
would be interesting to investigate that direction. I mean, again, this is stuff that I have done pretty much in isolation, and I had only 2 or 3 people helping me from time to time. So, I mean, this is why I wanted to present it here. I mean, something like this would be interesting to see. I mean, we could see where we can apply this thing and where we can't. And this is something that is completely open today. We don't know.
Yeah,
but it's a very good point, yes.
So the transition in your talk between the mathematics of the Wigner representation and kind of a description of that in terms of particles, signed particles, but it wasn't clear to me exactly what the connection was. So the best I understood was that for every point in the phase space, you would associate a separate particle, and the sign you would assign to that particle would just be associated with the sign of the Wigner representation of the
Yes, yes, it's more or less like this.
So you have an infinite number of particles associated with what we would normally consider a single particle, because assuming that your Wigner representation does not have compact support, but
Oh, okay, yes, yes. Then you would have an infinite number.
Of particles.
Yes.
So this idea, so if you had said, rather than just associating a sign, if you said I associate a real number, so the whole amplitude, whatever that real number is, then the idea would seem to me very reminiscent of a few kinds of interpretations that are out there. So there's one called the many interacting worlds interpretation of quantum mechanics.
Okay, well.
And the idea there is, so if you're familiar with Bohmian mechanics,
Yes.
Bohmian mechanics has particle configurations, and it has a pilot wave, which is a wave function. And the pilot waves guides the particles around, but the wave function also determines the initial distribution. So there's a kind of tension between the two roles of the wave function in that interpretation. So some people say, well, it would be very nice if we could think of the wave function as really just being a description of a distribution.
Mm-hmm.
And so if you say, well, it describes an ensemble of systems, then the idea is, well, maybe we could sort of reify that ensemble, make them all real and have them interacting with one another, and then you've kind of replaced the wave function with this ensemble of particles. So that seems kind of reminiscent to what you're doing here.
There are similarities for sure. Actually, if I had more time, I would have been very interested in investigating that direction. For example, another thing that I can see is that there are connections with other formulations also. But
to my mind, the things you should look at, so many interacting worlds, go look at those papers.
Okay.
That seems closest in spirit to what you're doing. And then Lee Smolin has something called the real ensemble interpretation of quantum mechanics, where he does something very similar, and he says, rather than thinking of this as an ensemble, only one of which is real and the other of which were only possible, assume that they're all real, and then try to replace the wave function with this real ensemble of things. So those strike me as the interpretation approaches that are closest to what you're doing here.
Well, thank you. I will definitely have a look at those interpretations. I mean, if I can find connections with other things, it's always interesting. So thank you.
It strikes me that your focus has been on largely on the computational aspect.
Yes, yes, yes.
To discretize this, to use the...
It was our first goal.
Yeah. Okay.
So.
And so in doing that, you're going into a discrete representation, and so you're no longer having that infinity of virtual particles.
Yes.
Because now you have sites on which you can have virtual particles, but you're discrete in both position and momentum space, and so you've got a finite set of particles or virtual particles that you're dealing with. And so from that perspective, it seems that you may have something that's quite powerful to work with. So computationally,
at least, yes.
Be able to do that. But as soon as you go to the continuum, as Rob was saying,
it's going to be a completely different story. Yes, yes, yes.
And so there's your computational power has disappeared.
I see your point. It might be the case. Thing is, I don't know again, because many of these things were just done.
Now, coming back to my earlier question about identical particles, fermions, bosons, really the inclusion of spin is necessary in order to address it.
So this is also why I wanted to show you this, because I think there is still a lot that has to be investigated there. This is just the tip of the iceberg in my head. But since we can see there are at least numerical advantages, it might be interesting to see, to understand it better.
Absolutely. But as soon as you get to something like the hydrogen molecule, you've got 2 protons and 2 electrons now, and so spin becomes consideration in seeing what...
Well, all of this was without spin, of course.
Okay.
Actually, this was one of the next thing that I wanted to do, but they cutted my financial support in Europe, so apparently they were not so interested.
I mean, because you have the phase space, right, interpretation, even in QM, you can take into account spin by just using symplectic geometry.
That would be one way to go, but again, I need time or I need help. So like I can tell you, for example, speaking of numerical advantages, when I've done like this experiment here, if you do this in a, let's say, an EGF time dependent, okay, which is a huge equation, you can do this. People in the US are doing things like this. You obtain the same results, but you need a supercomputer. This experiment, believe it or not, I did it on my $300 netbook. And this is what you see. It provides the same results. So to me, there is definitely some advantage here, at least in terms of computational, let's say, resources. But the theoretical part is something that is completely obscure to me and needs a lot of study.
Does anyone else have any more questions? Right, let's thank you.
Okay, well, thank you very much.